Do you know what 27 million pounds of moving steel actually sounds like in the dead of the night? Muskingum Mine, Cumberland, Ohio. 1974. The midnight shift. A freezing, miserable drizzle falls across a desolate, deeply stripped landscape. At the very edge of a crumbling 150-foot high wall, the Bucyrus-Erie 4250W, universally known as Big Muskie, is moving heavy overburden. This is not merely a construction machine, it is a mobile industrial facility. It is a walking skyscraper. The veteran operator, sitting in a small, illuminated control cab suspended stories above the dark mine floor, drops a massive 220 cubic yard dragline bucket into the blast muck. The bucket alone is the size of a multi-story house. As the massive steel drag ropes violently pull the bucket toward the machine, it swallows 325 tons of shattered earth in a single, brutal 60-second pass. The physical scale of the machine dominates the gloomy Ohio skyline, but the true, terrifying engineering violence happens entirely unseen. To hoist that immense payload from the pit, the machine's internal electrical system draws staggering, unprecedented power from the local grid. 18 1,000-horsepower electric hoist and drag motors spool up simultaneously. The sudden, violent demand for electricity causes the voltage on the entire regional utility grid to visibly drop. The lights in surrounding farm towns literally flicker every single time the giant bucket bites heavily into the earth. The regional power company was forced to install dedicated, heavy-duty substations and a massive 138 kilovolt transmission line just to handle the transient electrical spikes created by this single machine's relentless dig cycle. The power draw was equivalent to a small city of 30,000 homes, surging and dropping every single minute of every 12-hour shift. But managing the electrical supply was the utility company's problem. The operator sitting in the freezing cab faced a far more immediate physical limitation regarding the massive steel rigging. The Bucyrus-Erie 4250W was officially rated to move 325 tons per pass. To translate the raw, screaming electrical power of the generator room into physical digging force, Big Muskie relied on massive steel wire ropes. The drag ropes, responsible for pulling the giant bucket through the shattered earth, were 5 solid inches in diameter. The hoist ropes, responsible for lifting the loaded bucket into the air, were similarly massive. On standard engineering paper, the tensile strength of these ropes far exceeded the rated payload. But the clean mathematical models generated by Bucyrus-Erie engineers assumed a fluid, uniform digging motion through perfectly fragmented material. Down at the Muskingum Mine, perfect fragmentation was a complete myth. The bucket frequently struck dense, unblasted seams of solid sandstone or immovable limestone boulders buried deep in the overburden. When a bucket the size of a duplex apartment, traveling at high speed and backed by millions of pounds of electrical pull, suddenly arrested against solid rock, the massive shock load transferred directly into the steel drag ropes. If the operator simply watched the analog load meters on the console, they were already too late. The heavy meters suffered from mechanical latency. By the time the needle spiked into the red danger zone, the 5-inch steel rope had already exceeded its physical elastic limit. A snapped drag rope on a machine this scale was a violent, highly lethal event. The recoiling steel cable could easily slice through heavy support equipment or severely damage the machine's internal hoist drums, costing the mine hundreds of thousands of dollars in catastrophic downtime. To survive a long night shift without destroying the heavy rigging, the veteran dragline operator had to become a physical extension of the machine. The control cab of the 4250W was located far out on the right side of the main housing, providing a commanding view of the deep pit floor, but completely isolating the operator from the mechanical heart of the machine. There was no direct mechanical linkage between the control levers and the drag drums. The inputs were entirely electrical. Yet, an experienced operator did not rely on the lagging analog dials. They drove entirely by the subtle acoustic and physical feedback transmitting through the massive steel structure. When the bucket struck a buried sandstone seam, the sudden violent resistance traveled 300 feet up the heavy drag ropes, through the fairlead sheaves, and deep into the superstructure. Before the load meter needle even twitched, the high-pitched scream of the drag motors dropped violently, producing a deep, guttural hum that reverberated straight through the solid steel floorboards of the cab. Simultaneously, the enormous twin tubular boom would visibly shudder against the night sky. The veteran operator felt this microscopic change in vibration right through the heavy soles of their work boots and the seat of their chair. In that split second, they instinctively pulled back on the drag levers, instantly dumping the heavy electrical current and bleeding off the tension before the 5-inch steel rope exceeded its breaking strain. This sensory baseline, the ability to physically feel the precise difference between normal, heavy digging resistance and a fatal shock load, was completely undocumented in any Bucyrus-Erie operating manual. It was tacit, hard-earned knowledge gained through thousands of hours sitting in the seat. But once the bucket was safely loaded and hoisted, moving 27 million pounds of steel in a massive circle became a brutal lesson in rotational physics. Big Muskie was mounted on a massive circular tub, 105 feet in diameter, providing the base for the gigantic swing gear. When the operator engaged the heavy swing motors, the superstructure accelerated, carrying the 310-foot boom and the loaded 220 cubic yard bucket through the freezing air. The centrifugal force was absolutely staggering. The loaded bucket acted as an immense, heavy pendulum. If an operator swung the machine too aggressively and then braked abruptly to dump the load on the massive spoil pile, the forward momentum of the heavy bucket would continue, exerting an extreme lateral pull against the point sheaves at the very tip of the boom. This heavy side loading was highly destructive. Dragline booms are engineered primarily for vertical compression and lifting strain. They are structurally vulnerable to violent lateral twisting. To prevent twisting the long boom or ripping the heavy swing rack right off the tub, the veteran operator had to catch the bucket. They executed a precise, undocumented maneuver known as plugging the swing. By gently reversing the heavy electrical current to the swing motors just before the bucket reached the exact dump point, the operator created an invisible electrical braking force that perfectly counteracted the forward momentum of the swinging load. The machine, the boom, and the heavy bucket arrived at zero velocity perfectly simultaneously, floating motionless over the spoil pile for the exact second required to release the drag ropes and dump the dirt. But moving the dirt was only half the battle. A machine weighing 27 million pounds simply cannot roll on tracks. The immense ground pressure would shatter heavy steel crawler pads and sink the entire machine deep into the Ohio mud. To reposition along the high wall, Big Muskie had to walk. Bucyrus-Erie equipped the 4250W with 4 massive, hydraulically operated steel shoes, each measuring 65 feet long and 20 feet wide, positioned in pairs on either side of the main housing. When the pit geometry dictated a move, the walking sequence began. It was not a continuous drive, but a slow, agonizingly heavy lift and drag procedure. The operator engaged the massive internal hydraulic pumps. The heavy steel shoes lowered to contact the earth. As hydraulic pressure built to unprecedented levels, the entire 13,500-ton tub lifted slightly off the ground, tilting backward. The machine then dragged its heavy circular base backward along the mud, setting it down precisely 14 feet away. The massive shoes then raised, moved forward, and prepared for the next grueling step. The machine moved at a top speed of less than 10 feet per minute. While the heavy mathematics of the hydraulic displacement were perfect in the Bucyrus-Erie design logs, the physical reality of the Muskingum Mine floor was far less stable. The earth beneath the shoes had to bear the highly concentrated weight of a small skyscraper. The engineers designed the massive hydraulic shoes to distribute the 27 million pound weight to a ground-bearing pressure of about 22 pounds per square inch. But in the rain-soaked Ohio fire clay, bearing pressure calculations frequently failed. If the soft ground gave way under one shoe during a lift, the entire massive machine tilted. A list of even a few degrees on a 310-foot boom created terrifying structural torque on the swing rack and the massive circular tub. To prevent this catastrophic twisting, the 4250W never walked alone. It was preceded by a dedicated fleet of heavy Caterpillar D9 bulldozers that spent their entire shifts doing absolutely nothing but grading and compacting a perfectly level surface, known as a pad, for the massive dragline to walk on. The veteran operator had to feel the firmness of the earth through the heavy hydraulic pressure gauges before ever committing to a full step. As the massive shoe lowered, the operator monitored the hydraulic resistance. If the pressure built asymmetrically, indicating that one side of the shoe was sinking into unstable mud, they aborted the step instantly. They would lift the heavy shoe, signal the bulldozers to push more dry material into the void, and wait. The machine demanded absolutely perfect geology to move. And ironically, despite moving mountains, Big Muskie never mined a single ounce of coal. It was strictly a heavy earth stripper, designed exclusively to handle the massive overburden of the Muskingum Mine. The coal seams in Ohio were relatively thin, but they were buried under up to 150 feet of dense rock, heavy shale, and clay. The 4250W walked along the top of the high wall, ripping away the landscape and casting the heavy waste material into the previously mined cut, thereby exposing the black coal seam far below. Once the coal was exposed to the sky, a completely separate fleet of smaller loading shovels and heavy bottom-dump coal trucks drove into the pit floor to extract it. Big Muskie was the vanguard of the entire operation. The production targets of the mine depended utterly on the dragline's continuous availability. If the dragline stopped, the coal fleet below soon ran out of exposed seam, and the entire downstream supply chain to the power plants ground to a halt. But dragging a 220 cubic yard steel bucket through abrasive sandstone 24 hours a day creates immense, destructive friction. The high tensile steel of the bucket was rapidly consumed. The teeth, the lip, and the massive bottom-wear plates were subjected to constant, severe abrasion. Replacing a 230-ton bucket was simply not an option for routine maintenance. It had to be rebuilt on the fly. The mine employed dedicated welding crews, whose entire operational purpose was to climb inside the massive steel structure during scheduled downtime and apply hard-facing weld to the highest wear areas. Working inside the bucket of the 4250W was exactly like working inside an enclosed steel cavern. The mechanics fought the clock, completely enveloped in thick welding smoke and the sharp smell of ozone. They dragged heavy welding leads across the caked mud of the pit floor, rebuilding the bucket's structural steel inch by inch. When the bottom plates wore too thin, the maintenance crew required massive external rigging and multiple heavy cranes just to physically flip the 230-ton bucket over to weld the underside. The physical maintenance of Big Muskie was a heavy industrial operation in itself, demanding a logistics chain that rivaled the digging effort. The Bucyrus-Erie 4250W proved that moving literal mountains was mathematically and mechanically possible. But if the machine was so relentlessly effective at exposing coal, what external force ultimately forced it into a permanent, premature shutdown? Big Muskie did not fail mechanically. It was rendered completely obsolete by legislation. The Muskingum Mine produced high-sulfur coal, perfectly suited for the regional power plants of the era. But with the passage of the Clean Air Act amendments in the early 1990s, burning high-sulfur Ohio coal became a severe environmental and financial liability. National energy demand plummeted as power plants shifted their supply chains to the low-sulfur coal flowing endlessly out of the Powder River Basin in Wyoming. Big Muskie was an absolute engineering marvel, permanently trapped in the wrong geology. It weighed 27 million pounds and was entirely powered by a fixed electrical umbilical cord. It was vastly too massive to be disassembled and relocated across the country to a new, profitable coal seam. A machine built to operate for decades suddenly found itself stranded without a market. The utility company ran the harsh, unforgiving mathematics of surface mining. They realized the massive electrical power draw, the escalating maintenance costs of the heavy rigging, and the massive overhead of the dedicated bulldozer fleets could no longer be justified by the rapidly shrinking market for Ohio coal. In 1991, the operators powered down the 18 hoist and drag motors for the final time. The Bucyrus-Erie 4250W sat completely idle and rusting against the Ohio skyline for 8 long years. In 1999, it was officially deemed an environmental and liability hazard. Demolition crews moved in with heavy explosive charges and cutting torches, completely dismantling the 27 million pound structure for scrap metal. Only the massive 220 cubic yard bucket was saved, left behind in an Ohio field as a hollow monument to a defunct era of extreme, unapologetic surface mining. What the maintenance records showed about how it had been operated, how the veteran operators read the heavy drag rope tension right through the floorboards, how they precisely plugged the swing to save the boom, how they felt the ground give way under the massive hydraulic shoes went with the operators when they retired. Some of it was written down in informal shift logs. Most of it wasn't. The high wall is still there. The Ohio ground is exactly the same. The machines that mine it now are a tiny fraction of the size, and know absolutely nothing about the sheer, terrifying scale of what was learned on it.